Okay, so in this video, we're going to very simply implement some exploratory data analysis in Rstudio, and we're going to make reference to our code that I've adopted from Dave Langer and from Varian. I'll just give you the links there. Dave has a lot of R code and Python code and so on, a lot of very interesting explanation here. And I strongly recommend that you have a look at not just the lessons he's prepared for Titanic, but a whole range of different videos and playlists that are here that are very, very useful for data science in general. The other source then of interest is Varian's paper, which is probably something of interest to people more from an econometrics background who typically would use R, but he does some analysis here, introduction to machine learning for Titanic and some other data sets, and we'll make use of his machine learning R code. Okay, so just to set this up then, it's going to be an exploratory data analysis. It's going to make use of Tidyverse in particular, machine learning, C3 from Varian. We're going to set out a confusion matrix just to measure the degree of error and the accuracy of some fairly rudimentary machine learning, right? Just to introduce the machine learning area. Okay, so we're going to try and bridge between then exploratory data analysis and then gently try to introduce some machine learning. Okay, first thing we need to do then is just copy our code. We'll go in and copy, right? And then we will open up Rstudio. So here we have an instance of Rstudio, and we have a familiar environment, the console, global environment, and then where we would have our packages and also where our plots would appear as well. So to load in our code, it's very simple: file, new, our script, and then we'll Control V, and our code has gone in. And I've tried to set up the code in such a way that we just need to, I've left explanation around each section, but we need to just execute, and we can execute by running. And the first line of executable code here is install package, and we're just loading in basically data for the Titanic, the WSWR, that's in our environment here, and we bring it in by installing. Now, we didn't have to install, I already had it in, so I reinstalled and then made it available in the environment using this command library PASWR. Okay, also very important here is the Tidyverse suite, which is made up of both the dplyr, ggplot2, and there's a full set of packages here for all kinds of data manipulation. In particular, we'll use ggplot2 and then the dplyr for data manipulation and ggplot2 for visualization. Those could be installed individually. We won't do that here. And I've left some annotation here where we're getting some of the other places you might get the titanic3 data from. There is a data set available from HAL's portal there on the Journal of Economic Perspectives, but we're going to get our Titanic3 data set in from this package. That makes it kind of neat and compact. And we can take a look at the data then in the environment. So where did we get this from? We got it from the PASWR package. And then we're going to refer to the Titanic3. We're going to create a new object called Titanic, right? So that'll mean in our global environment up here, we have the Titanic3 data set. And if we investigate, we can see sort of spreadsheet or two-dimensional table with columns and rows. Each row represents a separate passenger, and then we have sex, age, sibling, spouse, parent, child, the ticket, the fare in pounds sterling, cabin number, embarked, Southampton, Cherbourg, and Queenstown are the 3 points of 3 ports passengers embarked from. Boat, body, home destination. So we're probably not going to use these last 3, right, in this particular analysis. Okay, we go back in. We can also make that available just by hitting View Titanic, right? So it appears again. So that's just another way of accessing, or just come over to the global environment, double click, and it would come up. Glimpse is a tidyverse verb. We can get a sense of what's in our data set. P class is considered a factor, but survival is an integer. Probably we'll try to change that to a factor in a moment. For some of the graphing in Tidyverse, we need survive to be a factor, just to do some of the ggplot2, perform some of the ggplot2 analysis. First and foremost, we're going to focus on survival, and of course we would like to know the number, the percentage of individuals to survive. So we'll take the full number of rows in the Titanic data set, we'll sum the survived, so it's zeros and ones, and then we divide by the 1,309. What we observe is 38% survived. Sometimes it makes sense that when you're creating a variable, right, when you're doing some data manipulation or going to change your data set, maybe put one on ice. So we're going to create this new object Titanic before factorization, or before we impose categorical classification on some of the data we have here. So we're survived, we're going to change to a category variable, but before I do that, I'll just put this to one side, right? And that's just basically to say, look, before any changes were made, we have the Titanic3. Now I could read in, I suppose, Titanic3, right? But Titanic before factorization, that will do that. And then if we glimpse here, we'll see there's a few here are considered integers. And maybe we'll just make sure that they're factors. So we're going to change the P class to a factor. Already is. Survive is going to be a factor. Sex is a factor. We'll make sure that's the case. And then Titanic3 embarked is a factor. Okay, so we're only really making one change there. Glimpse again, and you can see we've converted survived into a factor. Okay. Okay, so we can go again here. Let's just set out a series of questions. Now, the approach that I have here is following fairly closely Dave Langer, at least in terms of just posing a question, you know, what was the survival rate what was the survival rate that we had, right? And then we'll look at what was the survival rate disaggregate for male and females, and then, you know, what was the survival rate by passenger class marked on ticket. So these are things we would like to see. We'd like to see how the variables interact and correlate. I'm not going to perform a correlationgram here, but I am going to inquire what was the survival rate subject to something else happening. So the survival rate for male, female, survival rate for passenger class, for fare paid, and so on. These are the things that may present, would be of interest to us. Okay, so first initial graph then we're going to run here is just a basic ggplot where we make reference to the Titanic data set, and we just want to do a bar chart where those who survived, those who drowned, and you can see those who survived are in a minority, those who drowned are in the majority. And then we would like to do a table of those who drowned. There was 809 who drowned, 500 who survived. If we add both of those together, right, you can see that makes up the full complement of 1,309 passengers. Okay, we could say, look, set up a small table. Tabling is important, and later on we'll have a look at some pivot tables for investigating, just to break apart data. Pivot tables are a nice way to format large amount of data and put it in a succinct way which can be read clearly and concisely. Okay, so we might like to add some labels and themes here on this. It won't make enormous changes, but we can say, look, we'd like a title, passenger survival rates, and then passenger count, and then classification, whether the individual survived or not. That just makes it a little bit more readable, and it's always good to do with visualization. What was the survival rate broken down for male and females, right? So we know from the films that males somehow did a little bit worse compared to the females in terms of survivorship. The women were given priority getting onto the lifeboats. When we look here, we just have the breakdown of males to females. Overwhelmingly, there was more males aboard than females. By changing survive to a factor, right, what that allows us to do then is to add an additional layer into the graph here, so that we can color code and we can see what proportion of the male survived, a very small proportion, what proportion of the female survived, one has survived, much large proportion of females survived, relatively speaking. Okay, so this is, if you like, the survival here is our target variable, and we're trying to look at how survival correlates. Now, I'm not doing formal correlation estimation here, but I am looking at how one variable, the survival target variable, interacts with the other variables before I start any type of formal modeling. Okay, so this process is a little bit exhaustive in the sense that we can run through and do a lot of analysis, and that's kind of what exploratory data analysis is about. It really is about getting to know what's in your data set. And what we've done here is now we're going to investigate along passenger class what was the survival rate. Again, if we had left out this bit here, let's say if I cut and had ran that graph, that same ggplot syntax, it would all be gray. And by leaving it in, Control V, by having field survived, what that does, it allows us to create an extra layer of nuance in our graphs. Now we have the labels and the titles and so on, which is very good in terms of the visualization. That's important that we have that there. But we can see first class passengers survival was higher than for second class as compared to third class. So first class passengers, perhaps not too surprisingly, do better here. And then we might want to know what was the survival rate by class of ticket. So you might say, for instance, passenger class, right? And so it's first class, second class, and third class. Recall passenger class and sex. We can leverage the facet commands to further segment the data. Okay, so sometimes we would like to go a little bit more, bifurcate, if you like, a little bit more the data that we have. And in addition to, let's say, just running this basic syntax with the bar charts, what we would like to do is break this apart for passenger class. So create separate graphs for the passenger class. So it'll be first class, a graph, a second class, a third class, and then we've the male and the females. Okay, so we basically use sex. Before it was P class, now we're going to say sex, but filled by survived. We did that before. And we just add this facet wrap here. And that says break the previous graph, if you like, or the graph before down so that we can splice out or divide by class each graph. Okay, so that's a very powerful result, and it's useful then for examining what's going on. But we can see if you're female in first class, female in second class, your survival prospects are really good. If you're female and third class, it's not awful compared to the males. It's only 50-50 though, and much worse than the first class females and the second class females. First class males, second class males, third class males do quite badly. Their survivorship is very poor. Probably first class males come out the best here, relatively speaking. What was the distribution of passenger ages? Okay, so we run another ggplot, and this time it's going to be a histogram, and we label the y-axis with passenger count, and then we break underneath into buckets of 10-year bands, right? So if, for instance, we change the bin width to 5, which might provide us, this is kind of a way of customizing our graph, and this is the nice thing about the ggplot2, we can easily adjust the syntax to pull out what it is we want. Now we've more definition in terms of narrowing the buckets, but maybe you'd say, I actually like the 10-year bucket. That's more interesting to break down individuals in their teens, in their 20s, in their 30s, and so on. So if you run that, again, we get this type of, we can see that most of the passengers, you know, large bulk of them are in their early 20s, right? That age seems to be typical profile for people traveling. Then you might say, okay, great, but is there any discernible pattern in terms of age related to survival? And because we have fill as a factor, survived as a factor, we can break out the nuance then simply by introducing fill, right? So again, the graph we had before, and if we just add in fill equal to survived into that same graph. So let's copy, go back to the previous one, and just put here, Control V, and run that again. You can see the effect of fill here is to give us that extra definition. Now we don't need it here because we have it below. And we can examine the degree. Is there any relationship then between age and survival? Right, so we've the distribution of age. That's a very nice graph to have. And then we can look at survival. It doesn't jump out, but as it turns out, younger people did do a bit better in terms of survival, right? But if you're in your 20s, not really, right? In your 20s, not so much. But for the quite young, survivorship was a bit better, and in the machine learning, we'll be able to establish some splintering there in terms of age bracketing, right? But if we run logit models, unfortunately, that age mightn't be statistically significant. Okay, another great visualization tool then is box plots. And what they provide is kind of a distribution where we get a median, we get the different quartiles, we get a maximum, and then you get outliers. And the median is the typical. It's not the average, it's the typical fare, or it's a typical age. And we're interested here, of course, in doing a ggplot and pulling out a box plot, box and whiskers, and then looking at age, right, for those who survived compared to those who perished. When we look at it at first glance, we can't really see any discernible major difference between the two. So we actually have to be more, we have to drill down a lot deeper actually to examine that, and we will see it eventually. And you get that from actually just doing the basic humdrum drilling down and exploring the data. So exploratory data analysis is really designed not to be a quick fix, but actually to throw the measuring ruler over the data set and to pull out the key trends, but does involve a little bit more type of forensic analysis. The modeling at the end can be quite slam dunk, and you're looking to set up hypotheses and test them, and then test levels of accuracy and how well your model is predicting. But the EDA, the exploratory data analysis, is where you really get down dirty with the data and you try to pull out what are the key trends, key themes. Okay, so in this graph, we pretty much doing the same again. It's the Titanic data set that we're going to use. It's a GG plot. We're applying the syntax. We want on the x-axis, we want the passenger class. On the y-axis, we want age. So we've got that. We've also got a facet wrap here for the different sexes. That's why we've two graphs here for female and for male. We're looking at age distribution by passenger class on the Titanic. Okay, so that goes in as a key, that's a title. And then the label passenger class on the x-axis, age on the y-axis. What we have then is, you can see that the median age for people in first class was a bit higher than those in second class compared to those in third class. And possibly what we're getting here is a preponderance in third class of younger people, maybe in their 20s, who are emigrating. And then wealthier people who can afford to travel in luxury. Older people can tolerate that quite well. So we see the age distribution tends to be wider for first class, right? Especially the older groups. We get slightly more preponderance of older people and a bigger preponderance of younger people in third class. And it might be that third class has more economic migrants. So we're getting the median value. So the thick bold line going across is the median. The median value of age for first is higher than for second, higher than for third, and like that. Likewise, if we find that for the females, we see survived is 1, drowned is 0, more incidents of drowning. It also should be noted that there's 263 rows removed because we don't actually have the age for 263 of the passengers, right? So we're not seeing everything here, but we're seeing what's available. 263 individuals didn't communicate, or it wasn't recorded their age. So these are empty cells in our data set. Okay, it's an interesting application of box plot, and it's a bit revealing in terms of looking at the distribution of age for males and females and across the different passenger classes. Okay, calculate the mean and median. Okay, it's very important that we maybe have some kind of sense what was the you know, the mean and median age for the different individuals. So for instance, we have first class, second class, third class, female and male. And you can see 37, 36, then 26 for second class female. Average age is 17.4, and then in third class 2022. Okay, so when we look at the median age here, it's let's see, we have the mean, the average age, right, and the median age. So they do correspond pretty much, right? Now we can't make direct comparisons really against the graph here because when we look at our data here, we don't disaggregate in terms of what we have, if you like, is we have survived is 1 here, right? So these are the individuals who survived. So that would be the blue. And what we have here is we didn't break it apart for survived, didn't survive. We just do that by coloring. So the numbers here are aggregations of what we have over this side. There is some correspondence in terms of the average and the median values. And then when we compare for the different classes, it's true that the male and females 36, 37. Okay, we can see that here in the male and females. and then it's younger for the females and males in second class, right? We're not getting median of 26, but then we're just looking at the passengers who survived here, right? And then we have below then 20. So the median and average ages for second and third class is less than for first class, right? That's fairly clear. Okay, if we go to the next, we're taking those who drowned. So before we created a table for those who survived, do the same table for those who drowned. Now this is a form of pivot tabling, if you like. And again, we observe those who, in this instance, drowned. The males were older, 43 on average. Then the second class females, female and male, 34, 33, and then female and male, 23, 26. But this is the group when we say filter the data so that survived is equal to 0. That means we're just interested in those who drowned, and the table above, those who survived. Okay. Now, in a business, as a communicating business intelligence or scientific intelligence, this type of pivot tabling can be quite powerful. And we might want to save that, and I'll show you this in a moment, how you might be able to save out a particular interesting pivot table that you might have that merits some discussion. We could try to graph that then with a distribution. I think the histogram is probably a little bit more powerful in terms of getting a little bit more precision here in understanding of what's going on. But basically, if we look here, what we have, we're doing this ggplot. It's a histogram. The bandwidth is 5. We could make it a bit bigger. Okay, we want to leave it at 5. And we're considering age of the passengers, right? So we're looking at the age distribution. We're doing a bifurcation of those who survived. So survived is 1, drowned is 0. And then we've broken it across the different classes. So what we observe basically here is most females in first class survived. Interestingly, there must have been one very young female who drowned, and then some other marginal cases. For the males in first class, it's a mixed bag, but those who are really young did well here. So if you're male in first class, not great overall, but if you're young, and there's not that many of them, they did tend to survive. That wasn't true for this female here. For female second class, the very young survived. The very young survived. For male second class, the very young survived. So age does seem to be a factor, even though we didn't get it from the initial box plot. And then female third class, their prospects weren't awful, but not great either, I suppose. And then male, those who survived, the younger ones probably did a bit better. And then awful, if you're in your 20s or older, you tend to do very poorly. Okay, so this type of disaggregation of the data is a very powerful visualization, and does reveal that age here somehow is a factor, right? Age, if you're very young, especially in first, second class, you were surviving. There is an exception, not sure what would have happened here, right? Maybe a very young baby, we can imagine how that could happen. Baby might be lost in the panic. A small human being mightn't be so visible, and maybe in the crush, so on, things could go awry. But for third class then, probably the younger ones are doing a bit better, proportionately speaking. But it's only the very young. And then the bulk of people being young here compared to out here, I don't think you have such a great advantage, right? If you're male, second class in your 20s, not really tremendous advantage by being younger here compared to here, right? So age may not be such a big factor there, going between the 20s and the 30s to 40s. But then if you're a male who is 3 years old or 2 years old or a few months, your survival prospects are excellent. How does fair, proxy for class and sex influence survival? make use of pivot tables. Okay, so we're going to do a few quick pivot tables, but initially, just to summarize, we want to get the mean fare overall and the median. And you can see the mean fare is 33, but the median is 14. So there is quite a bit of skew here, suggesting that maybe a couple of the passengers paid outrageous fares, and the bulk were paying much less. So the median fare is substantially less than the mean, suggesting skew. There would appear to be a large discrepancy between fares paid by men and women. Okay, let's examine that. When we run it, what we observe is the male, and we get the mean, and then we compare it with the female. So we filter the data using the dplyr syntax. This is Tidyverse dplyr syntax. And we can see the mean fare for women is 46, the mean fare for men is 26. So that's quite a discrepancy. Let's do the same, but use median for males initially using filter, sex equal to male, and then filter sex equal to female, estimate the median fare for women. Median fare for men, 11. Median fare for women, 23. Again, substantial discrepancy between the two. Don't know why. It's a bit of a, it intrigues me a bit, such a wide discrepancy between females and males. Okay, pivot table allows us to explore large data sets of data interactively. Once you create a pivot table, you can quickly transform huge numbers of rows and columns into meaningful, succinctly formatted report. Okay, so that's the big benefit of pivot tables, and we can explore them, right? Where we're looking at the P class and then break it down female and male, and then look at the mean fares. And in each segment there, the males are paying substantially less than the females. That's on the mean fare. And we can do the same again for the median fares, break it apart for P class, passenger class and sex, get the value of the median fare in each of those categorizations, and then do a count of the number of individuals in that classification. Let's view that, and you can see again the females are paying more than the males, paying more second class, and the median ticket for the female and male. The women are always paying more, and then we've quite a few, the numbers, you know, we have enough numbers to stand over with confidence that it's not just a few exceptional cases, but this just seems to be the norm at the time, and it kind of intrigues, but I don't have a good explanation. Explore how does class, sex, and fares influence survival. Okay, so we're going to throw in here into the mix more, and we're going to say, look, can we examine did this have any effect in terms of survival? And we might have a look at those who drowned, those who survived, and so on. So what we've done is we've added an extra element of dimensionality here. And can we say that the fare somehow influenced survival? Maybe, perhaps. When we compare the males, yeah, those who survived were paying a little bit more. What about the females? That's not true for the females. And we can go down through those. Now, when the dimensionality increases, you really have got to spend a bit of time, and that's worth doing. But maybe, probably, you would download Excel, and then focus on the area for a little while. Again, we can do the same and do it for this time the median fares. And can we observe those who paid more survive? Well, that wasn't true here. I can't see that. The females here, 0, she drowned. There was 5 of them in that category. The median fare was 151. And then for females, the median fare for this 139 was 80. So we can't say because you were paying more, it coincides or correlates with higher survivorship. What about in third class? If you're paying a little bit more, let's have a look at the females. Well, those who paid this 14.8, right, median fare, there's a pattern here. They were drowning more than females who were paying the cheaper fare. So when we disaggregate like this, we don't directly observe straightforward relationships between paying higher fare in the different classes, and that the performance, the survival prospects of those who are paying more was greater than those who are paying less. Can't see that here, and it's not really evident for the males either. Okay, worthwhile getting down into brass tacks there and drilling into it. Okay, proportion of passengers embarking from each port. Let's take a look at that. 914 passengers got on in Southampton, 270 got embarked from Cherbourg, 123 embarked from Queenstown, and there was 2 we don't know where they came from, right? And then we have the proportions here. Again, that's a nice table, and it's worth exploring. Now, did it have an influence in terms of survival? And okay, there's 2 passengers who got on, we don't know where. But then the Cherbourg passengers on average seem to be paying a bit more than the first class in Southampton, and Queenstown second class. Now, how many passengers got on in Queenstown? Only 3 got on in Queenstown in first class. They paid 90. The average fare for Southampton first class was 72. Average fare 106. Maybe just indicates the longer distance, right, and the extra meals coming from Cherbourg. Do we observe that all the way? 23, Queenstown 11, Southampton 21, second class. So you can see second class fare average was 23, not that much higher than Southampton. Second class fare, Queenstown was 11, good bit cheaper. Third class average fare was 11 from Cherbourg, 14 from Southampton, and then 10. So again, there isn't a clear pattern. The numbers, of course, some of the numbers are a bit low here in terms of the passenger relating to particular classification. So maybe we can't really observe too directly, make strong statements about any particular grouping here, right? But no overall strong pattern coming out, except maybe you're paying a bit more coming from Cherbourg compared to the other points of debark, other ports from where passengers embark from. Okay, pivot 5, more analysis like that, but just using the median fare. And we can examine the link between fare, point of departure, survival, and these become quite substantial then, and are worth downloading and exploring a little bit more in depth. So we'll go over, because we'll try to capture that in some visualization. Now, this pivot fare 7, if I wanted to investigate this, I would just write out to the pivot fare 7. So we'll just make sure session set working directory to choose directory, and I'll probably put into the desktop here. Now, when we look at the desktop, just desktop, we don't have a pivot fare 7 file there. That's okay, but I'm going to set that as the source, as the directory. So when we write CSV pivot fare 7, that will save then to that directory, and we can go in and we can take a look then at the desktop for a moment and see, okay, the pivot fare 7 then appears there as a CSV file. So if we open that up, right, we can see our data can be recovered. So we could save it down, save in the location that afterwards we can go back, take it, maybe if we do have an interesting pivot table that we can examine a little bit more in depth. Okay, let's go back into Rstudio again. So, okay, it's clear that men paid more than women and were less likely to survive. We can do a scatter graph that presents that. Now, this is following type of syntax that I saw on DataCamp, so I thought I'd leave the link here for people if they wanted to go back and explore a little better. And it also, I mean, that's an interesting in its own right. That's an interesting visualization of a scatter graph. We've the fares and then we've the age. But again, with Tidyverse, we can create layers of information here. And we could say, why not break apart the same graph, but have males and females so that we can see, okay, look, it is true. There is a preponderance of females paying more. The red, who denote females, they're paying more. And then males are paying substantially less a lot of the time. Maybe there was a preponderance of males in third class, but even so, males in third class paid substantially less than, on average, than females in third class. And that seems to be true right across the way. We can break that apart then again. So put in a facet wrap for survived. So we can look at here, those who drowned, those who survived. And again, more females survived, and you can see more of the, you know, on average, they seem to be paying more. Again, that stacks up against the pivot tables we've been working on. We could, what was the role of the family size? And what we're going to do, what is the role of the family size before family is, okay, and we're going to put in family as a column, right? So before family is a size is introduced as a column, right? So we're going to create a new variable, right? And we're going to put that into our data set. Now, if we glimpse again back at the Titanic3 data set, there is no column here for family size. But what we're going to do is create a new variable, family size, based on sibling and spouse, parent and children, and then one. So if I am a passenger on the Titanic, that would be one. And then if I was asked sibling and spouse, so the number of siblings and spouses, and then the number of parents and children, right? That then would be the full family unit, and we could record that then in this family size. So let's create that variable. And then let's look again at our data set and see, can we see that there's a family size column now introduced? It is. That family size has now come in and could be useful then in trying to understand survivorship. Okay, so we're going to try, we can now try to find a link between family size and survival. It's clear very large families were fewer, right? So the very large families were a little bit less in evidence, but we suspect that that might have an effect on survivorship. And when we look at this family size and put it on the x-axis, break it apart then for males, females, first, second, third class, what we observe is in first class, we don't have those very large family sizes, right? There was the biggest here in first class. You can see family size 6 or around 6 didn't do that well compared to the rest, right? By and large, the females just did well here. Family sizes on the whole probably tend to be smaller, right? Most people didn't have families, right? But some did, and some had larger families. When we come to second class female and second class male, there is a bit of a change here. The family size does grow a little bit, but those with the larger families not surviving that well. And then in third class, we have these really larger family sizes. Now, they tend to be rare, but where we have situations of having larger families, they don't do well in terms of survival, right? Across the board, the larger families here, they don't survive for male. Something similar for females, a small little bit of blue here denoting some survivorship. But by and large, these larger families are not doing well in terms of survival when we look across the board. So family size may be relevant here. We can imagine a situation where as the families become quite large, there may well be not a place on the lifeboat for everybody, and then there's a horrendous choice that's got to be made: which child survives, which child drowns. Most parents probably would find that a very challenging type situation, and might revert to, well, it's fairer that we all go down together. Right. So, okay, we can imagine some of the rationale here, but there may well be other rationale. It might be, look, just it correlates with class, right? There's a stronger correlation with class, these larger families. Okay. Next thing we're going to look at here is just do a little bit of introduction to machine learning based on HAL Varian. And we're going to start off by taking each of the, we're going to take our data set and isolate out each of the columns and create variables, right? So sex is going to be, we're going to subset it out from the Titanic data set, and likewise age and class, survived, and siblings and spouse, right? And we're going to install our part, which is for decision trees, and then make that available in our library, right? And then we're going to run a model, a very basic model, where we say, look, create a decision tree where we model survived in relation to class and age, and then output. And there's a little bit of an optimization waiting here. We can change that, and we can observe the effect of doing that. Now, to graph, we'll install our part plot, make it available in our environment, right? And then to run this model, just to view what's been estimated here, we apply this syntax or part plot. Now, you might have noticed that there was a stop sign here, which means that the installations was still ongoing. We would like to visualize the decision tree. So let's just put that out. And what we get here is, remember, 0 is drowned, 1 is survived. And if you're third class, yes, 528 out of 709 drowned. If you're not second class, you're first or second. So if you're not third class, then you're first and second. And no, again, if you're greater than 16, no, that means you're first, second class, and you're less. So we're going no to the right. No means then you're the opposite to this condition. You're less than 16, first and second class. 34 out of the 36 of those survive. So age seems to be a factor here, and survivorship improves dramatically if you're younger. Now, we didn't put in here sex, we just said class and age, and then we're modeling that with survive. When we come back, if you're yes, greater than 16, you're first, second class, greater than 16. If you're second class, yes, first class is going this way. Well, 193 out of 315 survived. If you're second class and greater than 16, not great survival prospects here. 157 out of 249 drowned, right? So that's a nice way of doing that. Now we could put in, for instance, include in here sex and see what appears, run the same type of, this 0.38 is how much pruning do we want. We don't have to reinstall again. We just have to run our model. And this time, what's happened, it's the sex has gobbled up all the explanatory power. So if you're male, you're no, that means you're female. Most of those, well, a good substantial chunk are surviving, otherwise drowned, right? Now we can lower this 0.38, maybe lower it to 0.2 and run that again. Right, and then come down and plot and see what we get. Okay, then increase it to 0.5, 0.5, run that again, right, and then plot. Okay, turn off our graphic, do it again. It would appear, even when we adjust for pruning here, if we include insects into the model, it's just gobbling up most of the explanatory power, right? So again, if I revert back, if I remove sex and just rely on class, we're getting a different output, right? A different type of explanation of what's going on. And that's back to where I suppose we had started. So I can put back into 038. But you can manipulate a little bit the CP here on this for optimization and for pruning, right? And see what you get. Okay, graphics off. Let's just remove that. Then it goes off, and then we go into C-tree. So the C-tree identify the structure of branches using a sequence of hypothesis tests. C-trees consequently require only light pruning. The C-tree presented below initially divides by gender. The second node then divides by passenger class. The third node divides by age. And then we form bins which graphically depict the proportion who survived following a given set of conditions being met, right? Okay, so let's just now installing the party package is a little bit more involved. Okay, let's say we do want to do that. Now, I didn't have to do it because actually, as it turns out, that package was already there in my installations, right? So if I had searched for C-tree, I would have found it here. The fact that I'm installing it again means I'm going through a basic, a fairly substantial type of installation. If you do this, set this install packages up on the Google console, you're going to find as well that it's going to take a while for the installation to take place. Okay, so that's took about a minute or so. Let's make it available in our environment. And we can just see, is it here in our packages, C-tree? Actually, party. Okay, so party is a package here. And by virtue of saying library party, I'm making it available in this environment and it gets ticked, right? So if I remove the party here in terms of the little search engine, you can see all the packages that I've installed, right? Now we want to run a C-tree where I'm explaining the survivorship, and I'm using just P-class, sex, age, sibling, spouse. These were the variables that stood out the most when we did the analysis, right? Okay, now the C-tree, let's run that. And this is a form of machine learning. So it's basically, we're coming, perhaps we could do this without even going through the EDA, and it automates that process. So the exploratory data analysis that we went through is labor intensive, involves a lot of eyeballing, setting up pivot tables and going through. What the machine learning does, and one of the great powerful features of machine learning is it can take a large data set, it can the algorithm can crawl over the data, and then we can you know, create this type of logic in terms of predicting survivorship. So again, 1 is survived, 0 is drowned. And basically this tallies with what we had before. If you're male, actually we go, if you're female and you're first and second class, you're most likely going to survive. If you're female but in third class, it's not that good. If the family size, if the sibling spouse is less than 2, your prospects are way better than if you're greater than 2. So again, back to that idea that at the margin, family size could be very important, particularly if you're in third class. If the sibling spouse exceeds 2, your survival prospects, even though female, very, very poor. If less than 2, it's 50-50. If you're in first and second class, excellent. If you're male, first class, less than 54, you have less than 50%, less than 40% chance of survival. But if you're greater than 54, it's even more appalling. So again, age seems to be important there, but at the margin, the numbers here are not insignificant. 151 in this bucket and 28 here. If you're male and second and third class and less than 9 and less than 2 in your family, your survival prospects are excellent. okay? But if your family size is greater than 2, your survival prospects are awful, right? So again, age, we can look here at how the variables interact, and the C tree captures that, and it does its own type of pruning. We don't have to apply pruning here because the hypotheses that are created are sort of a test of the strength of the split, and it's a kind of automated pruning taking place, and it's configured here in such a way that the tree is self-pruning, right? The C tree, the conditional inference tree, is self-pruning, but we can see age is important, but at the margin, right? So if you're male, if you're second and third class, if you're less than 9 years old, and the small family size, the sibling spouse is less than 2, yes, good prospects of survival, but greater than 2, poor prospects of survival. If you're older than 9, very poor prospects of survival, right? And there's 624 in that categorization. Okay, so the C tree is a very powerful way of very quickly arriving at some way of organizing the the order of priority, the order of influence that variables exert on our target variable, which is survivorship. We want to predict survivorship, and we can clearly delineate pathways that would say, yes, if you satisfy these conditions, chances of surviving are very high. If you're female, first and second class, chance of surviving quite high. And then at the margin, we can look at the size of, the number of siblings and spouse in a family unit, how that militates against survival, the age, how that militates against survival, and so on, right? If you're less than 54, greater than 54, satisfying some other condition, age has an effect, right? And that's something that we're able to glean from this machine learning approach. And this is a good way of trying to understand what machine learning represents and how we would bridge, how we would go from exploratory data analysis, where we eyeball the data very closely, and then apply a lot of effort in terms of trying to discern the patterns, or allowing machine learning to automate that process and to pull out what are the key variables that are determining in terms of survival, right? Okay, so that's other things then we could look at then is check the accuracy of the model. So we could say, look, if we create this model, then could we predict survivorship and create a new object called titanic3, right? So I have a model, and then I could say, look, I want to predict the survivorship. So I could take the entire data set again, run it, and predict survival. And then I could say, let's tabulate that. Let's take the Titanic predictions, compare against actual survival, and create a confusion matrix. So I'll abbreviate that as an object Titanic conf, right? Which is a tabulation, if you like, of survival, and then Titanic conf again, just to print it out and see what we get. And what we have here is the prediction. So maybe we could center. So again, confusion matrices are a very clever device to get some kind of sense of the true positives, the true negatives, the false positives, the false negatives. So we have error here. And what we might note, if we look at the variables, might just come down a little bit. Let's remember, this is the actual, right, on this axis, and then the predicted. So if I add the 697, that's 697 plus the 112. If we add those, we should get the 809, right? Remember, we had 809 who drowned, and we had 500, I think, who survived. I think it was so if we take the 143 plus the 357, and run that, sugar, come down, we take that and execute that, it should be, I think it's 500 straight. Okay, so originally we know in the data set there was 809 who drowned, there was 500 who survived. Okay, now so these are the actuals who drowned, the actuals who survived, but then the prediction is we're predicting a true positive that's 357. Okay, so to understand a little bit better what's in the confusion matrix, let's just bring in a confusion matrix descriptor, and I'll just pause here, bring that in. Okay, so this is what I have up on Vinegar Hill Data Labs, and it's just basically to explain a little bit what's going on with the confusion matrix. The 357, again, remember with the 143 and the 357 add up to give 500. And so that's the actual who survived. And then the actual negative is those who actually drowned. So when we add up the 697 and the 112, we got the 809 who drowned. And the true positives, if you like, are those the model predicted. This C3 predicted that 357 were true positives predicted to have survived and actually survived. So using our C3 model, the C3 prediction from using the C3 model, it actually predicted that 357 survived and actually survived, right? So predicted to have survived and actually survived. Now the model also predicted 112 to have survived but actually drowned, and that we call a false positive. So the 112 here are false positives. It's an error in the model. We have false negatives, 143 false negatives. That is, we predicted, the C3 model predicted 143 passengers to have drowned, but they actually survived. And then the true negative, the C3 model predicted 697 to have drowned and actually drowned, right? So on the diagonal here, we have the correct. Off diagonal, we have, if you like, the error embedded, right, in our model. Now, if we want to evaluate model performance, then if we added up the 112 and the 143, right? So if, again, if I just go underneath, if I want to add the 112 plus the 143, that is giving us the amount of misclassification in the model. There's 255 from the confusion matrix that were passengers that the model misclassified. Okay, now we can eyeball what the model predicted, the C3 model. So if I just go Titanic predict based on what we had here and run that, this is the output that I have, right? So this is what the model was predicting. Again, noting 1 is survive, 0 is drowned. And then Titanic $ survived is what actually happened, right? And that's for the 1003 passengers. Again, there's some misclassification going on. This is the actual data, right? So here it is true. This is what actually happened. The one we observed before is what the model predicts, right? And then if I want to just take the confusion matrix data and add the off diagonals. So if I want to add the off diagonals, these variables here, right? If I run that report out, I'll also get 255. Okay, so that's a measure then of model accuracy using confusion matrices, and we'll touch on confusion matrices again. Okay, but it's a good way of evaluating a classification accuracy for a model where we're trying to predict a binary outcome.